Hello and welcome to lecture 14 of the microelectronics lab. In this theory module, we will talk about the nanoscale thermal characterization with thermo-reflectance imaging. We will give you a brief introduction to why thermal imaging is needed. We'll talk about the basic working principle of different thermal imaging techniques, particularly the thermo-reflectance imaging. Then we'll explain the setup and the measurement flow. We'll talk about different imaging modes in which you can do the thermal imaging, transient mode, steady state imaging modes, and so on. We will discuss the steady state imaging and transient mode imaging in detail. And then we'll also talk about the software features. How do you calibrate acquired data, analyze and process all the data, and use it for scientific investigations.
Hello, I'm Rajarshi Roy Chaudhary, and I welcome you to this theory lecture session on nanoscale thermal characterization using thermo-reflectance imaging. This presentation will be structured as follows. Firstly, we'll talk about the effect of heating in semiconductor devices and why we would need to characterize them. Secondly, we would then introduce thermo-reflectance imaging technique by comparing this technique with other standard thermal imaging techniques. In the introduction to thermo-reflectance imaging technique, we'll try to understand the key central concept in this imaging technique, that is the thermo-reflectance coefficient. After gaining an understanding of thermo-reflectance coefficient, we'll talk about the thermal imaging setup, various components that are involved and how they interact with each other and how they enable us to carry out a thermal imaging measurement. Then we'll talk about the measurement flow, which begins with the calibration process, and after calibration we'll talk about the various measurement modes. The thermal imaging tool has two modes of operation. One is transient thermo-reflectance imaging and the second one is steady state imaging. In this talk we'll talk about various concepts associated with these two measurement modes. Finally, we'll talk about the software control part of this tool, which involves how to calibrate using the software, and we'll talk about image acquisition and analysis processes, software processes in details. Finally, I'll highlight some references which one can refer to for a detailed study of this tool. So to begin with, let us understand why we need to monitor heating or why thermal imaging is necessary. When a semiconductor device operates, especially scaled devices where the operation involves presence of high electric fields and high carrier densities, the regions of high electric fields might trigger generation of heat. In fact, the major energy loss route in semiconductors is by the route of heat generation. What happens if heat generation occurs in a device? If there is excess self-heating in a device, then that leads to an inevitable rise in the lattice temperature. When the lattice temperature rises, it can affect the device properties in the following ways. It can modify the carrier properties, it significantly affects the carrier transport, it modulates the electric fields in the device, and then it also induces material degradation. Which further triggers the device towards a catastrophic failure if this forms a positive loop. That is, if the modification of carrier properties and field modulation further leads to heating, then this loop continues until and unless the device fails. Moreover, if we look at it from the reliability perspective, in addition to catastrophic failure, the mean time to failure reduces by half if the device temperature increases by even 10 degrees centigrade. One can see here the mean time to failure versus junction temperature. This plot shows that if the temperature rises from say 160 degrees centigrade to 180 degrees centigrade, a device lifetime reduced by an order, in this case from 10 to the power 7 to 10 to the power 6 hours. This is because the failure in these devices is governed by some processes which are activated by energy. So this activation energy determines that a certain temperature is required for these processes to start, and therefore it is always dangerous when the device temperature rises, because this can trigger all these failure processes, which further leads to catastrophic failure. Therefore, it is very important for the development of robust devices so that these devices can be made reliable for further use in electronic systems. Therefore, it is very important to monitor how the heat generates, what are the factors on which this heating would depend, and how we can mitigate this heating. And therefore, it is very important to have the thermal imaging done of the devices under stress conditions, electrical stress conditions. Okay, now that we understand that it is important to monitor or characterize heat generation, let us see what are the available methods for thermal imaging. One of the common methods is infrared thermography, lock-in infrared thermography. Also, for very high resolution measurements, micro Raman thermography technique has been deployed very recently. In this table that we see here, we compare some of the existing thermal imaging techniques with the technique of our concern, that is thermo-reflectance imaging. So before we do the comparison, let us understand on what aspects we would be comparing various methods. So when we are doing thermal imaging, what are the factors or what are the things that we would want to know? We would want to know the location of heating, that is, where is the heating happening? What is the magnitude of the heating? That is, how much temperature rise or how much heat generation is happening in those regions? And what is the kinetics? That is, how fast the heat generation happens, how fast the heat spreads, etc. So we want to know these three things: location, magnitude, kinetics. So what are the requirements? Like the tool that we are going to use, how will it give us these three parameters? What are the requirements? Like when do we know that this tool will cater to our needs? So location of heat generation means we have to detect hotspots. So we need high spatial resolution. We need a tool which will provide us high spatial resolution. Magnitude, to properly detect magnitude changes in temperature in the lattice, we need a tool that would provide us high temperature resolution. That is, it can detect a very small delta T or change in temperature. And regarding kinetics, so once we know location and magnitude, we are left with kinetics. We have to understand how the heat spreads from one part to other, or how is the heat carried away from the device. So that is done if we have a tool which has transient imaging capability. That is, if we can monitor temperature of various regions of the device versus time. Okay, now that we understand that we need to have high spatial resolution and high transient imaging capability, let us compare this and high temperature resolution. Let us compare various methods. We see that the first column here is position, that is the delta X value, the distance to which our temperature information can be resolved. And we see that thermo-reflectance and micro-Raman spectroscopy thermography technique offers the least resolution, and even thermo-reflectance imaging allows us to go even to a higher resolution than micro-Raman. So 250 nanometers to 500 nanometers of resolution can be achieved, spatial resolution. Moreover, if we look at temperature resolution, thermo-reflectance imaging temperature resolution is at par with the IR thermography technique. Therefore, we can achieve higher temperature resolution in addition to the higher spatial resolution which was not achievable in the standard techniques. In the standard IR technique, we see that we have higher temperature resolution, but we do not have high spatial resolution. Now regarding the transient imaging capability. So what is the time resolution with which we can capture images? We see that if we compare it with IR technique, thermo-reflectance order has a 1 order lower delta T value, that is, we can capture events at a scale of 0.1 microseconds. So thermo-reflectance imaging, if compared with all the other methods, is the best in the class in terms of offering spatial resolution, temperature resolution and temporal resolution. Best numbers as compared to the other techniques. Okay, now that we are talking about transient images and spatial resolution, let us have a feel for the numbers that are involved. So thermal transients depends on multiple factors that we'll discuss later, and the temperature ranges could be of this order. The transient could have very fast component which could be of the order of 10⁻⁻12 seconds to slow components of the order of 10 seconds. The device dimensions could be from the range of nanometers to hundreds of micrometers or higher, depending on whether you are characterizing nanoparticles or you are characterizing high power transistors with long distances. Okay, so we see that thermo-reflectance imaging is suitable for our measurement given its high spatial, temporal and temperature resolution, because it helps us monitor temperatures in miniaturized devices where localized hotspots are present. So with this understanding, let us compare thermo-reflectance imaging with infrared imaging in terms of a sample image. The sample image shows that the infrared image, so this is basically a resistive heater with a metal coil-like structure. So if you look at the thermo-reflectance image as current flows, the coil-like structure is resolved very well, and we can see that it is of the order of a micron, the spacing. So this is not well resolved by the infrared image. Infrared image shows an average temperature in this region, but the thermo-reflectance image shows the temperature to be confined along the resistive coil, and therefore it shows how thermo-reflectance image can offer us high spatial resolution, which helps in detecting localized hotspots. Okay, so now let us introduce thermo-reflectance imaging technique. Thermo-reflectance imaging technique is a sensitive lock-in measurement technique wherein we measure the change in material's reflected light pixel by pixel. So what happens is, let's say this is the device and this is my active region of operation where the device electrical excitation is applied. So as a result of this electrical excitation, the device gets heated up. So here we utilize the change in refractive index of this material, the material which responds to the electrical signal by heating up. So we measure the change in refractive index due to heating, which is seen as the change in surface reflectivity. So when temperature rise happens, refractive index changes, and that is reflected, that is manifested as a change in surface reflectivity. So this process is coupled, delta T and reflectivity is coupled by a coefficient called thermo-reflectance coefficient. So larger delta T would mean larger change in reflectivity, as governed by this formula. So what is thermo-reflectance coefficient? So we understood that thermo-reflectance coefficient determines how much delta T would lead to a change in surface reflectivity. So this coefficient is a material parameter. So for a given material, the coefficient would have a fixed value. So what is the origin of thermoreflectance coefficient? Why would a material have a thermoreflectance coefficient? It is because, so if you talk about metals and semiconductors, they have energy bands. Temperature rise in these materials, semiconductors or metals, would lead to change in the band properties, which modifies the dielectric constant epsilon r, the permittivity, and which then subsequently modifies the refractive index and surface reflectivity in these materials. So the surface reflectivity can be expressed as a function of the real part and the imaginary part of the complex refractive index, and therefore it can be shown that delta r by r, which is CTH into delta T, this CTH becomes a function of the real and the imaginary part of this complex refractive index. Therefore delta r by r is a function of the refractive index, which is a function of temperature rise due to mediated by the band property change, temperature induced band property change. Therefore delta r by r is related to temperature via this thermoreflectance coefficient. Okay, now that we understand the origin of thermoreflectance coefficient, let us look into the various properties of thermoreflectance coefficient. So this is a material parameter, but it depends on the following factors. The illumination wavelength. So what is meant by illumination wavelength? I'll go back to the previous slide. So we saw in thermoreflectance we are measuring surface reflectivity, so we are shining light, we are checking the amount of light reflected back. So this light wavelength governs what the CTH value would be. Okay. Second is, so let us see the plot of CTH versus wavelength for some standard metals. So if you look at this gray curve, this is for aluminium, which peaks at 800 nanometers. That is, if someone uses a light of 800 nanometers wavelength and shines it on aluminium, then using 800 nanometers wavelength, you can have the most sensitive, you can detect the most sensitive change in temperature. Whereas if you use a lower wavelength or a higher wavelength, the sensitivity of the surface reflection to temperature reduces. Similarly, for gold, we see that there are two peaks, one at somewhere below at around 480 nanometers and the other near 532 nanometers. So what happens when we get a new material? We have to, whenever we get a new material, we need to find out the regions where the thermoreflectance coefficient would have peak, because these are the wavelengths which can be used to detect small changes in temperature or accurately capture temperature changes, because these are the wavelengths in which the device reflectivity is a strong function of temperature. Okay, so in addition to illumination wavelength, CTH or thermoreflectance coefficient depends on the material temperature. That is, so in the expression, if we go back and recollect, so delta r by r is C into delta T. I have not, there's a small mistake here, there should be delta r by r is proportional to delta T. So this proportionality assumes that C is constant over a large delta T. That is, delta r by r versus delta T is a straight line. But that may not be true for a large range of temperatures. This can be true for a small range of temperature. Because with strong increase in temperature, the rise in temperature would again lead to second order changes in the material property, and which would then bring in non-linearity. That is, delta r by r would no more be linearly proportional to delta T. So we have to operate, so we have to find out a region where this linear proportionality holds. Thirdly, the CTH value depends strongly on the material processing. Although it is a material parameter, that is, it is constant for gold, say it is at 532 nanometers, it would be -3, -4 for gold. But then it depends if you have a passivation on gold, on top of gold, or if you have some kind of a coating, protective coating, or if the gold processing has resulted in very rough surfaces or globule formations, then these might lead to deviation from the value shown here. That is, you might be expecting -3, -4, but because of your processing effects, because of the presence of passivations and coatings, for example, this is a big challenge in devices where we have to give passivation layers for protection from the atmosphere. So there the coefficient value changes, and therefore whenever you are using a new material, it is very important to find out the value of the thermoreflectance coefficient. Okay, so now that we understand the origin of thermoreflectance coefficient, let us understand the thermoreflectance imaging setup. So in this slide, I'll show you the various important components of the thermoreflectance imaging setup. In the left hand side image, we see a full view of the thermoreflectance setup. The thermoreflectance imager is housed in something called a Faraday cage, and it sits on a vibration isolation table. Why is Faraday cage important? Because it shields the device from external unwanted electromagnetic radiations. Why is vibration isolation table important? The vibration isolation table will isolate the device from the ambient vibrations which might propagate through floors and other rigid regions. This thermoreflectance imaging, it is imperative to mention at this point, the thermoreflectance imaging is a pixel by pixel imaging technique. As I said that it measures reflection, surface reflection, so I must tell you that surface reflection from one pixel by pixel surface reflection measurement is done. Therefore, if there is a vibration which creeps into the during measurement, then that would lead to the shift of pixel, and that would lead to inaccurate calculation of surface reflectivity. Therefore, vibration isolation is very important. So we have, in addition to this imager sitting in the probe station, we have a control panel. This controller panel has three parts: sand scope, sand source, and sand controller. This controls the light sources, and it houses the LED trigger and the device and the test trigger panels, which we will discuss in details, both in the demonstration session as well as in the subsequent slides. And lastly, the third segment, we have the central processing unit, which controls the acquisition and analysis software. Okay, so now let us zoom into the imager hardware. So if we peep into the probe station, we see that there is a CCD camera sitting on the microscope. Objectives are present here, and the CCD camera operates from 365 nanometers to 800 nanometers with 60% more than 60% with 60% quantum efficiency over this range, and therefore we can take measurements in this setup in the wavelength range of 365 nanometers to 780 nanometers. In addition to the CCD camera, we have the micropositioners. The micropositioners make contact to the device, and electrical bias can be applied to the micropositioners. Then comes the objectives. The objectives are used to allow the light to be incident on the device, as well as to collect the reflected light. Okay, so in addition to these components, we have a thermocouple. The thermocouple is landed on the device to measure the surface temperature, and it is used during the calibration measurements, as will be discussed in the subsequent slides. We also see a specialized chuck. A chuck is a platform which holds the device. The specialized chuck sits on a piezo stage. The piezo stage is very important because it controls the XYZ movements as a device heats up, because whenever the device heats up there would be expansion in the devices which needs to be immediately corrected automatically through the software by the piezo stage. We also have a chip based heater because we need to calculate the CTH value, the thermo-reflectance coefficient value that I had discussed in the previous slides. So to calculate thermo-reflectance coefficient, this chip based heater is needed, as I will discuss in the calibration section. Okay, so this is the schematic of whatever I have discussed in the previous slide. We see the CCD, we see the LED source, and we see the microscope objectives with the optical path. So in the thermo-reflectance setup, electrical excitation is applied to the device, and at the same time the LED is triggered as well as the CCD is triggered. In response to the electrical excitation, the device heats up and its reflectivity changes. The LED shines the light. It measures the reflectivity by measuring the reflected light here in the CCD. So you see that there must be a phase locking between CCD measurement and the electrical excitation. So this phase locking ensures that you are capturing the temperature when the device is under stress. Okay, so if one looks at the thermal imaging characterization, it basically takes light as the input, because here light is incident from the LED source, and it takes light as the output because it is measuring, it gives light as the output because it is measuring reflectivity changes. Okay, so another important factor in this setup is the microscope objective. Okay, the microscope objective governs the spatial resolution. We saw that we need to achieve spatial resolution of around a micron or less than a micron, so this around 250 nanometers, 500 nanometers, of that range. So what governs the spatial resolution? The objective's numerical aperture governs the spatial resolution. Higher the numerical aperture, better is the spatial resolution. For example, in our setup, if we use a 100x objective with a 365 nanometers LED, then we can achieve 250 nanometers of spatial resolution. Okay, so let us briefly summarize the key features. The thermo-reflectance imaging is a non-invasive method. It just shines light, measures reflection. It uses a lock-in technique to synchronize LED pulses with the electrical excitation. What happens in lock-in technique? It enhances the signal to noise ratio, and it allows us to have multiple cycling of measurements done. Okay, most importantly that needs to be highlighted is that we are here using LED, light emitting diodes, as our optical source. There are some thermo-reflectance measurement methods like time TDTR, FDTR, time domain thermo-reflectance, frequency domain thermo-reflectance, which uses laser sources. Please note that our setup uses non-coherent LED sources in the range of 365 nanometers, that is UV, to 780 nanometers, that is NIR range. Okay, so with this brief overview of the setup, let us reiterate some special features of this setup. So in addition to the CCD, LED components and the objectives that I have shown in the previous slide, the piezoelectric stage forms an integral part of the setup because it helps us to counteract thermal expansion related shifts at nanometer scale. So say you are applying electrical bias to the device and the device active region heats up. In response to heating up of the active region, the device might expand. So the pixel map which the system had registered when the device was not heated up, so that it can compare reflection values at each pixel, the pixel map therefore which was stored in the under room temperature or ambient under non-heating condition, that will not be matched with the pixel map post heating or during heating, because the device might have expanded and therefore the pixel mismatch will happen. And this pixel mismatch, the system would then take it as change in reflectivity and wrongly attribute to it a delta T value, right? So to counteract this expansion, we need a powerful image processing technique which detects that there has been an expansion, and then it would instruct this piezoelectric stage to do the necessary corrections. So in addition to this thermal expansion corrections, the piezo stage also enables autofocus capabilities. That is, it allows the device to be always kept under focus by nullifying vibration induced errors. Because of vibration, there might be changes in the Z direction which might take the device away from our focus region. And therefore the piezoelectric stage enables capturing of accurate submicron thermo-reflectance coefficient as well as delta T maps, temperature maps. Okay, so now let us look into one practical aspect of the setup. So this thermo-reflectance tool is a self-independent measurement tool. That is, it can apply electrical bias. It can then measure the temperature change in response to the electrical bias. However, it can only apply biases to the range of 60 volts. But sometimes we might need to generate specialized electrical pulses, which may be high voltage pulses, which may be ultra short pulses, etc. So to do that, we might have to use some external pulse generators to bias our devices. As I mentioned in the previous slide, that phase locking is very important, that we have to apply electrical bias and we have to do the measurements when the electrical bias is applied. So how do you ensure phase locking, or how do you ensure that there is a coherence between your electrical signal and the optical measurement pulses? So to allow that, the thermo-reflectance control unit has an option called device trigger output. So this provides 5 volt trigger pulses which can then be used to trigger the external pulse generators. So this will ensure that the pulse generator will apply pulse only when the CCD is capturing your image. Okay. So given that we understand various aspects of measurement, including the need for external triggering, let us also look into, in addition to the hardware features, let us also look into the software features. So the MicroSange thermo-reflectance tool, which is known as the NT220C tool, it comes with 2 softwares. So there are 2 independent softwares. First is the data acquisition software, which is called by the name Sange View. And the second software is data analysis and image processing software, which is called the Sange Analyzer Plus. The Sange View has components such as Project Manager, Calibration Unit, Transient Imaging Unit, and Steady State Imaging Unit. The Transient Imaging Unit further has time series and voltage series capabilities, which we will be discussing in the Transient Imaging module. Okay, in addition to these components of the data acquisition software, we have the data analysis and image processing software. which is the SANS Analyzer Plus. It allows us to correct the calibration images for XY thermal expansion errors that might creep into the measurement. It then allows us to have an accurate temperature distribution map based on the corrected thermo-reflectance coefficient map. Further, it allows us to store the images in various data formats and allows us to generate AVI movie series based on the transient images. That is, you can have a time series view of the evolution of the temperature map. Okay, so with the hardware features and the software features in mind, let us try to understand and get an understanding of the steps of measurements involved. So the first critical step for the measurement is to get the thermo-reflectance coefficient value of my material, of the new material that I am going to use. So we have to select the wavelength, and then we have to estimate the C value for pixel by pixel, and this process is called calibration. Once the calibration is correctly done, we go to the acquisition, where we can use transient imaging, steady state imaging for acquiring the thermal images during electrical stress. And then we have the analysis and processing component. So we'll begin with calibration, that is estimation of the thermo-reflectance coefficient value. So the calibration and measurement flow is shown here. So for calibration, what do? We have to measure thermo-reflectance coefficient of my material, right? So if we remember the formula, that is delta R by R is C into delta T. What is unknown in our first step is C. CTH is my target. I have to measure CTH. I have to get the value of CTH. The CCD will measure delta R by R. Okay? And so if you know delta R by R, in order to get C, you have to know delta T, right? Then only you have two known values, and you can then extract the unknown value. So how do you make delta T known? You have to raise the sample temperature by a known amount. How do you do that? Let us go back to the setup. So if you look at the second picture here, you have a chip based heater and a thermocouple. Thermocouple is shown in the first picture, right hand corner, this red arm that you're seeing, and in the second picture, left hand corner, you see the chip based heater. So the chip based heater raises the temperature of the sample by a known amount delta T. The thermocouple measures this delta T value. Okay, so now that we know delta T, we have to also measure delta R by R. So this pixel by pixel measurement of delta R by R is done by the charged couple display, the CCD, that is housed over the microscope. So you have a pixel by pixel value of delta R by R, and you have a value of delta T. So you get a pixel by pixel estimation of CTH. So you get a map of CTH for XY values. Okay, so now that you have the CTH value by this measurement flow, you need to measure actual temperature rise during a practical stress condition. So again we go back to this working formula. Now we have CTH, and now delta T is unknown because we are giving an unknown stress. We are giving an electrical stress. So delta T is now unknown. In the calibration module, we had delta T known, we had delta R by R measured, and therefore we got CTH. In the measurement flow, we have to get this unknown delta T with the help of this measured CTH. The CTH has already been extracted experimentally, and so we have the CTH value per pixel by pixel. So what do? We apply electrical bias to measure temperature at our region of interest. So this electrical bias would lead to change in surface reflectivity because of rise in temperature, So again the CCD does this pixel by pixel measurement of reflectivity. So the CCD will give me this delta R by R now. We have the CTH value known, and therefore delta R by R by C would give me the value of delta T pixel by pixel. This is how we would generate a temperature map under an electrical bias conditions. Okay, so this electrical bias, it is important to understand that what are the type of biases that we can use. We have two distinct imaging modes available. One is steady state imaging, in which you can apply long DC like pulses to the device and measure the device response in terms of temperature. Secondly, we have transient imaging module, where you apply short pulses and you measure the temperature, temporal evolution of device temperature. Okay, so before we move on to delve into further details of these various imaging modes, there are some important points that needs to be kept in mind. That is, a proper wavelength has to be chosen for which the CTH value has a maxima or a minima. As I had shown in the calibration versus wavelength map, wavelength plot, that every material has the maximum or a minima like featured in the CTH value for a particular wavelength. So that proper wavelength needs to be chosen. That is very important. For example, if you have a semiconductor and if you are using a wavelength which is completely absorbed by the semiconductor, then that wavelength will give very weak thermo-reflectance signal. You have to select a wavelength where absorption is significantly lower and reflection has increased. Okay. So after selecting proper wavelength, we have to do calibration over multiple averaging cycles, because this calibration has to be done multiple number of times before generating a very good CTH map. This would be clearly demonstrated in the demonstration session, because the calibration, if you do not do it over multiple averaging cycles, it would lead to edge effects that creeps in because of various vibrations. So in the edges you would have contrasting CTH values. So it is very important that we do multiple number of calibration cycles. Okay, so although I have given the calibration flow chart, I will quickly reiterate the steps for calculating the thermo-reflectance coefficient. Number one, you have to use a heater to raise the temperature of the sample by a known delta T value. You have to select a wavelength, right? Because initially to begin with you do not have an idea that what wavelength would be good for my measurement. So you select a wavelength, then measure delta R by R pixel by pixel using the CCD. You measure delta T from the thermocouple, and then you estimate the CTH value. So this CTH value is for a given wavelength. Then you change the wavelength and you try to measure CTH, and by this way you try to find out the value of lambda for which the magnitude of the CTH is maximum. Okay, so that means the CTH value is maximum for a particular wavelength, and then that wavelength has to be chosen for your thermo-reflectance imaging measurement. Okay, so let us look into a semiconductor material to highlight that how one particular wavelength may not cater to all the regions of the device. For example, let us look at a gallium nitride wide bandgap semiconductor sample which has two gold pads sitting on it. So if you recall the CTH versus lambda plot for gold, it had a magnitude maxima at 532 nanometers. Okay, so the magnitude maxima at 532 nanometers means that you have to use green LED for providing maximum CTH value. That is, if you want to measure the contact pad temperature, then green LED has to be used. But then can you use green LED for measuring temperature in the gallium nitride sample? No, because the green LED will go through the gallium nitride sample down to silicon, to the substrate, whatever it is. Because gallium nitride is a wide bandgap semiconductor with a bandgap of 3.4 electron volts. So it can easily absorb 2.2 or 2.3 electron volts of radiation, right? So you have to use a near bandgap LED source, in this case which is 365 nanometers. So to measure the surface temperature of gallium nitride semiconductor, that is to measure the temperature distribution in this region, you have to use UV LEDs, because that will give you a high value of the thermo-reflectance coefficient. So this is the very first step towards the imaging technique. Okay, now let us look into the software module. So to do calibration, we have to open the SANG view module, which is the image acquisition software, where you have something called the project manager. So the moment you open SANG view, this project manager window opens up. Inside that, to the left hand side, you have various modules: steady state imaging, transient imaging, calibration, data analysis, etc. So the calibration module has to be used. Okay, so before we start the calibration, and when we start the tool, what are the things that we have to check? This will be again described in details in the demonstration session, but I will briefly right now highlight so that during demonstration you can understand it clearly. So the moment you turn on your system, you have to look at the various communications. Like, for example, is the software detecting your various synchronization timing modules? Is it detecting the CCD camera? Is it detecting the light sources, etc.? So you have to look for green lights in these corresponding to each module. Okay, once this is set, once the system has detected and is communicating with various hardware components, we have to go to the most critical part of the project manager, which is the illumination control. So illumination, this imaging has, as I said, is governed by measuring the change in reflection. So you have to ensure that there is proper illumination. So you have to play with the brightness values. The brightness has to be increased to allow enough illumination for a very good measurement. Good illumination would improve the signal to noise ratio. You also have the choice of choosing choice of wavelengths available here. So you have to select this drop down and you have to choose among a wide range of available wavelengths from 365 nanometers to 780 nanometers. Okay, so we then have to choose the frame rate. The frame rate means number of frames that the CCD will capture per second. So if you reduce the frame rate, that would increase the exposure time per frame. So you have to play with the brightness and frame rate as well as the gain factor for generating an optimum quality image, a good quality image. Okay, so now the moment you mount when you put your device, you also have to choose the microscope objective depending on the features in your device. If your device lengths are very small and if you have very fine features and you want to have a nanometer submicron regime mapping done, you have to obviously use objectives with higher magnification. Okay, so with this numbers set, we go to the piezoelectric control. So you see the piezoelectric control parameters are set here. So you have to click on center stage. That will ensure that the XYZ values, that the piezo stage is at the center, and you have to enable 3D motion so that it can have a live feedback of the shifts in the positional shift during measurement, and it can therefore correct those shifts. Okay, some indicator graphs. You have this focus level graph which helps you ensure that the device is well under focus, and there's an image histogram which also needs to be looked into while changing the brightness, because you have to ensure that the CCD count is well below 3000, because that would then saturate the CCD. This count has to be around just below 1000. It would be modest, like 754 is shown here. It's a modest number and it can be used, but you should not use a value of brightness which saturates the CCD, because that would damage the CCD. Okay, with these factors set, with these parameters set, let us go to the calibration module. The calibration module has multiple sub-modules. For example, to begin with, you have the hardware. The hardware allows us to set the chuck temperature. So in our case, we have a chip level heater, so which is TCAT 100, wherein you can vary the temperature of the heater, resistive heater, by varying the amount of bias applied. Okay, the microscope settings will be carried over from the project manager settings, and you cannot change it here. If you notice one more thing, that there's a number called distance per pixel. So this will give you an idea of the temperature information, that is over which region you are averaging the temperature. For example, 274 nanometers means that one pixel houses the information of 274 nanometers cross 274 nanometers area. So it will give an information of the temperature averaged over one pixel of this 274 nanometers value. Higher magnification means the distance per pixel would reduce. Okay. So now we move to the second sub-module, which is timing and illumination module. So for calibration, you have to heat the stage, right? You have to apply electrical bias to the heated stage that would heat the stage, and then the CCD would capture image as the device is heated up. This heating is uniform because the whole wafer is heated up, and you have to ensure that you give sufficient time for stage heating so that the device achieves equilibrium with the thermal chuck. So typically we use times of the order of 50 seconds, wherein the device is uniformly heated up and the device achieves thermal equilibrium with the stage, and then the CCD then acquires your images. It acquires 55 images in one heating cycle. So you can vary this number. Larger the averaging, better would be the signal to noise ratio. Thirdly, as the measurement goes on, you must keep an eye on this indicator, because that shows whether the brightness is sufficient for carrying out a good measurement. Okay. This is now that we have set the hardware, we have set the timing and illumination, we have to go to an important aspect of 3D alignment. So we had discussed about the piezoelectric stage. So the piezoelectric stage is constantly monitoring for any shift in the device. But this image processing, so this is done by an image processing software. The image processing software will detect a shift in the device, and then that would send a signal to the piezo stage, which would then control accordingly to bring back the device to its original position. So, but then how will the software know what is the reference? So you have to give an alignment reference to the software. So what do? Whenever we say we are probing this device, so this is a resistive heater again, and we are probing this resistive heater. We want to measure temperature distribution in this resistive heater region. So this is a metal, gold. So gold sitting on silicon oxide, and this bridge is of gold, which would act as the heater which connects these two pads. So we would look at the edges. So whenever you have a device and you want to do 3D alignment for the piezo stage to work well, you have to choose edges and corners or scratches in your device. Do not select a region which is uniform, because edges, if you select edges for referencing, that is the best detector of shift. If you are looking at an edge, you would be able to detect shifts very easily. So the software detects any shift in the device very efficiently if the reference is set in a region which has edges and scratch marks or some sharp features. Because the focus ROI chooses, the job of this focus ROI module in the alignment reference is to look for a shift, and therefore we would choose edges and marks where the shifts are easy to detect. So once we choose the focus ROI, we have to look for, we have to tell the device, tell this software feature, this software, that what is my device active region of interest. That is, what is my active area from where I want to measure the temperature. So that reference area would be selected by using capture reference. Okay, so we have selected focus ROI, we have selected capture reference, because this is the image that will be used as the original position for shifting back. So you have told the system, the software, how to detect shifts. You have told the software, okay, so if you have detected a shift, you correct the shift such a way that the device comes back to its reference. So the reference image is selected by the capture reference. So if you have selected, once you have selected focus ROI and capture reference, which is very important, you have to look into these numbers of alignment percentage and vibration filter. Higher alignment percentages of say 99% of these order means that the software will take measurement only when the alignment score is such that it is above, it is above 99% accuracy, or about this percent accuracy. You can select any value. If you lower the alignment percentage, that means you are allowing the software to take measurements even when there are vibrations. Okay. There is another number called vibration filter, which needs to be lowered to improve the alignment accuracy. So you have to increase the alignment percentage, you have to lower the vibration filter number to improve alignment accuracy. However, one must note that if you keep these numbers too very stringent, then the measurement would take a very long time. So you have to find out an optimum number in which the alignment percentages and filter numbers, the alignment score is good, as well as the measurement time is not too high. Okay, with these numbers set, we would then click on start measurement and the measurement would be carried out. So we also have, if you look at the second screen here, in the second screen, if you look at the right hand side, you can monitor temperature measured from the thermocouple, where the number of cycles, multiple number of cycles that you choose would be visible here. The temperature rise from room temperature to the heater temperature and then subsequent falling back can be monitored here. Okay, so how do you know that the measurement is going on? The status bar will continue to move. The system status will reflect heating whenever the stage is heated. It will reflect cooling whenever the stage cools down, and you have to ensure that these alignment score vibration indicator are green. If these are not green, if the device is not in focus, if it is not aligned, if the alignment score does not match your set criteria, then this would appear as red, and if this appears as red, then the measurement would be waiting. The piezo stage would try to correct itself so that it is able to match the alignment criteria. So if this is red, the measurement waits, the piezo stage is working to bring down the error within the acceptable range. Once it comes down, this again becomes green and then the measurement restarts. So then once the measurement is going on, you can select a region of interest. If you note here, there's an option called draw ROI. ROI is region of interest. You draw a region of interest. You monitor the thermo-reflectance coefficient. Okay, and the corresponding thermo-reflectance coefficient color map scales are shown here. Okay, so now that we have estimated thermo-reflectance coefficient, okay, I missed out a point. So if you have, once you have estimated the thermo-reflectance coefficient, you need to save it. So to ensure that all these, if you're doing multiple cycles, it is better that you have to monitor the ROI history, okay, before saving. So this option that you see beside the thermocouple is the ROI history button. So how do you know that your calibration is done? You must monitor the C value of the n+1th run and see how it is different from the nth run. So if the coefficient value after say 5 runs or 6 runs starts to saturate, that is, the coefficient predicted is now independent of the run number, that means that you can now stop the calibration measurement. How can you do that? You can monitor this in the ROI history. So this plots C value versus run number, and once this criteria of Cn+1 minus Cn is being low is achieved, then you can save your measurements. So if you click on save every cycle and give your saving path, then all the measurement cycle images would be saved in your desired folder. Okay, now that we have estimated the thermal reflectance coefficient for our material or device, we now go towards acquisition of thermal image. So in this section we will talk about transient imaging technique, we will talk about steady state imaging technique. So why do we need transient thermal imaging? Why not just capture a thermal image? Why is the time aspect important? It is important because we need thermal snapshot, because we need to monitor the transients, that is, we need to have thermal snapshots at multiple time instants during the heating and cooling cycles. This is needed because generally our device has multiple layers. For example, if you look at the left hand side schematic, again I'm showing a gallium nitride on silicon carbide device sitting on a packaged, it's a packaged device, so this package has multiple layers. This active semiconductor region is sitting on a die attach, which is then sitting on multiple other components of the package, which then goes to the PCB. So the active region of the device heats up, and then this heat is carried away through these multiple layers. So these multiple layers offers thermal impedances in terms of resistances and thermal capacitances. So you see, if there is a heating up happening, then the heating up or cooling down would be a strong function of these thermal impedances. Okay, and therefore you need to understand or predict the value of these thermal impedances, both within the active region and both across various layers of the package. It is very important to have thermal snapshots, because that will give us a very good information about the heating conduction pathways, and from that you can predict the thermal circuit, and which can then help you to remove those aspects, those components of the thermal circuit which are offering very high resistance. Generally in these devices, another practical aspect of why this is very important is, if you look at this image on the right hand side, gallium nitride semiconductor sitting on multiple other semiconductor layers. Say the gallium nitride region heats up, then you see the various other regions. Let us look at the substrate, for example. If you monitor the substrate temperature, the substrate would heat up at a different time scales. So the different temporary rise times would then be attributed to the different thermal boundary resistances, TBR resistances, which are present at the various interfaces of the multiple heterostructures. So therefore you must monitor, so therefore it is very important to monitor the dynamics of heating, the kinetics of heating. Okay, so now that we understand why thermal imaging, transient imaging is needed, let us look at the timing diagram. It is very important to understand the timing diagram in order to know that what are the parameters that we can play with while doing the transient thermal imaging measurement. So the first thing that I would like to highlight is the CCD. So if you go back to the project manager, And if you look at this number 3 in the left hand side, which I'm pointing out, this is the frame rate. The frame rate shows x frames per second. Okay, so now that means that for a given time frame you would have n number of frames. So if it is 30 frames per second, then one frame would be 1 by 30 seconds, and therefore that much amount of time would be this frame time. Let us say you have selected it in such a way that it is 33 milliseconds. You have selected the frame rate such that it is 33 milliseconds. Okay, so what is my goal? My goal is to apply electrical pulses to the device. And what am I expecting? I'm expecting that in response to these electrical pulses, the device current will rise, achieve a steady state. It may or may not achieve a steady state, it will rise, and then once the pulses are off, the device current will then go back. In response to the device current and electric field, the device temperature will follow a curve of this sort. The temperature will rise from the ambient room temperature to a higher value as the pulse is applied, and as the pulse is removed, the temperature would then try to go back to its original value. So what is my goal? My goal is to monitor, to capture this temperature waveform at a particular point in the device in response to this kind of an electrical pulse excitation. So what do? Whenever the device is heated up, you have to apply LED pulse, because as I said, the input in this imaging is LED pulse. So you have to shine LED to the device active region in order to monitor temperature. Okay, so if you want to capture this waveform, that means you have to shine LED at these discrete points. You have to shine LED at a point less than the starting value of the pulse. Then this LED will capture information of the preheating stage, right, when the electrical bias is not applied. Then you shift the LED pulse and you shine it somewhere during the rising stage. So like this, you keep on shifting the LED pulses. You shine the LED pulse at T1, T2, T3 time stamps T1, T2, T3, T4, T5 ... Tn. And at each LED shining, you are measuring the reflectivity, and therefore you will capture temperature at each and every LED time instance, right? Whenever the LED shines, you are getting the temperature. Therefore, what can you do? So first you have to capture just at the edge of the electrical bias, that is just before the electrical bias is applied. Let us number it as T0. So the initial LED delay, so this shifting of LED pulses, right, to scan over this temperature waveform, you have to shift the LED pulses by varying the delay. Initially the delay will be kept 0. That means, or say, the 0, if you select it as 0, it always starts with a value of, say, so let's say the pulse width is 50 nanoseconds, for example. Then it will always start with a delay value of -50, -25. Why? So -25 is the middle value of this LED pulse, right? So delay of -25 means you will get a temperature at this point, which is at this point. And then the incremental delay would be of the order of the LED pulse width, that you can always vary in the software. So as you tell the software, okay, now increment it by a value of 50 nanoseconds. So the first delay would be -25, the next delay would be -25 plus 50, that is plus 25. So you capture somewhere here. Then plus 25 nanoseconds more, then plus 25 nanoseconds more. That is how you get this temperature data. Okay. So what is the role of the CCD exposure frame? So you see, to get one temperature data, if you take one measurement, that would be full of errors. So you have to take multiple measurements at a one particular time instant and then generate one value. So we select a CCD exposure, a big CCD exposure, say 33 milliseconds, where the device excitation whereas is 1 millisecond. So you can apply 33 such pulses. not 33 pulses, rather 33 by 4, right? So you have to take into account the pulse period. So you can apply a certain number of device excitation pulses. And you select the delay to a particular value. Say delay value is, for example, minus 25 nanoseconds. That means in this frame of CCD, for all the excitations, for the n number of device excitations, you are going to measure temperature at the just before the beginning of pulse, and you're going to average this temperature value over the n number of excitations. So for the n number of averages, you're measuring the temperature at this time instant, and then you're getting averaging it into a one value. Okay, so once this value is obtained, the CCD exposure is complete, and then you move to the next delay. So you increment the LED pulse delay by an amount of delta t, a delay step of delta t. So now you are measuring temperature somewhere here. So this temperature at somewhere during the rising edge of the pulse. Okay, so you measure it again for n number of times, n number of electrical pulses. You measure it using in one of the CCD frames. You are measuring over n number of electrical pulses for a fixed delay, and then you are getting another value of the temperature. By this you can vary the delay like this. So LED delay for first 10 cycles would be here, for the next n cycles it would be here, for the next 10 cycles it would be here, and then by this you can generate this temperature transient. In this setup, what is the lowest achievable resolution? In our transient imaging setup, the lowest achievable resolution is 50 nanoseconds. Okay, so now that we understand the waveforms, we have to get acquainted with the various software control knobs that we have. So similar to the calibration module, we have this hardware part. The hardware part, we need not change anything. We go to the timing illumination module, where you have to choose device excitation pulse width. You have to tell the software that I am going to give an electrical bias of say 100 microseconds. What would be my duty cycle? Then this would determine my total period, right? Pulse width and duty cycle will give me the total period. 1 by period is frequency. You have the CCD exposure chosen by the number of frames per second in the project manager. In the project manager, you have chosen a value of the number of frames per second. So that gives you the CCD exposure value. That is what would be the length of this one frame. That value will come over here. That means if you choose the frequency such, the CCD exposure number such that it is 66 milliseconds, then an electrical bias of 1 milliseconds can be applied 66 times, right? It can be applied 66 times in order to generate the desired waveform, right? So these numbers would help you understand, like would be used to monitor the timing, to set up the timing diagram. Okay. Okay, so in addition to these parameters, how do we now vary the value of the delay? So we saw in the previous slide that the delay has to be changed, right? So one way of doing that is that you can vary this device. If you go to the device control subunit, you can type in your image delay value, and that will set or capture the image at a given delay. Okay, so before we move ahead, I would like to highlight some few more aspects related to these waveforms. That aspect, that is, I would like to highlight how LED pulse width is determined. So you see, if your device excitation is of say 1 milliseconds, and if you want to have a good information of the transient, that is the rising and the falling transient, that if you want to have large number of samples, then the LED steps have to be very fine, right? It has to be comparatively low, significantly lower than the pulse width. If the LED steps have to be lower, then the LED pulses, the pulse width have to be thinner. Accordingly, it has to be reduced. So how does the LED pulse width change? What is the software controlled knob by which the LED pulse changes? The answer is this brightness. So the section determined by brightness percentage, this knob has to be varied, which will then vary the LED pulse width. So if you reduce the brightness, then the LED pulse width reduces. If you increase the brightness, the LED pulse width increases. Remember, this number for a given percentage would be referenced to this device pulse width. Okay, so 94% does not always mean 17.7 microseconds. It will be different for different pulse widths. Okay, so then you would always say that, okay, I would always reduce the brightness because I would then have a low LED pulse width that will achieve very good temporal resolution. So you would always want to bring down the LED pulse width to 50 nanoseconds, which is the best that you can achieve in this tool. But then what is the problem with this? The problem is that if you try to reduce the brightness in order to reduce the pulse width, then the brightness indicator will show that the brightness is very poor. Then the overall signal to noise ratio of the images would significantly reduce. So the brightness cannot be reduced arbitrarily. It has to be reduced keeping in mind that the brightness is good enough for capturing a good high quality image. Okay, there is another aspect of measurement, that is this duty cycle. This duty cycle has to be kept low. Why? Because in these time scales of milliseconds, if you're exciting the device say for 1 millisecond, and if you're not giving it sufficient time before the next pulse arrives, the device may not cool back to its initial preheating value, okay, preheating stage, and then the next cycle would start off from an accumulated temperature. So you would see in the long run that there is an effect of temperature accumulation happening from the previous cycle, because you are not giving sufficient time for the device to cool down. Given the time scales are in milliseconds, you have to therefore ensure that the device pulse width and the duty cycles are such that the device has sufficient time for cooling down before the next excitation pulse appears. Okay, so this determines the duty cycle. As I also said that the CCD exposure is governed by the frame rate. Finally, the LED pulse width is governed by the brightness knob of the LED. Okay, now before going to the capturing of the full transient, the best way is to see if the numbers are correct or not, or the numbers are good or not. You would take one image at a particular delay value. That is, let us say you want to take an image when the device is at the edge, like when the full pulse has been applied and the temperature is supposedly at its maximum. So you would select that image delay value to be equal to that of the pulse width, and then you click on start measurement. So image delay value of 100 microseconds means that the CCD will capture the image at this edge, at the very last portion of the electrical pulse, when the temperature is supposedly at its peak. You capture this image and see if these numbers are creating a very good image or not. If not, then you have to again change these parameters and redo this. So once we are fine with these numbers and the image that we've obtained at a particular delay, let us see how we can capture the transient data, that is across the full time scale. So we go to this knob, this subsection called series. So you see there is something called create image series. So this will be again discussed in great details in the demonstration section. However, I will quickly highlight the parameters of interest. First is the average time per frame. That is, it determines the number of times you would want to average the image in one frame of CCD. As I have already iterated earlier, that higher averaging time would mean that the averaging is happening over a large number of images. And higher averaging time means one frame will consist of large number of thermal images which would then be averaged. Therefore, higher averaging time inevitably leads to a very good SNR, but it then slows down the measurement. The next parameter of interest is delay step. Delay step is this delta t value. This is the delay step. If you look at the right hand side, the delay parameters, like what would be the starting sample that you would want to measure, in the subsequent frames how would these temperature samples shift with time. For example, you would measure a t equals to minus 25, then you measure a t equals to 0, then you measure a t equals to plus 25 nanoseconds, then plus 50, then plus 75, plus 100, plus 150, like that you cover the whole excitation pulse width. So this number will be typed in here. Starting delay, current delay is when the measurement is going on, the current delay, if it is set at it shows the value at which time instant from the edge of the electrical excitation is the temperature monitored currently. Ending delay is after which step, which temperature data will the measurement stop. For example, 200 microseconds in this case. So let's say the pulse width is 100 microseconds, and ending delay of 200 microseconds means the device has gone through 100 seconds of electrical excitation and then another 100 seconds of cool off period, and then you stop the 100 microseconds and then you stop the measurement. So ending delay determines when the measurement will be stopped. So this delay is the the shift in the LED pulse in the subsequent cycle. So in the first cycle, the LED was at t equals to t0, as you can see in this graph. In the next cycle, the LED pulse is shining at t equals to t1. So this delay step is governed by these numbers: starting delay, ending delay, and the number of delay images that you want to select. Total number of images in the delay series. Okay. So this helps us generate a transient image, transient data. Okay, but this is at a particular electrical excitation. If you want to vary the voltage now, say for example this is at a particular voltage value, the another type of measurement that this software allows is to generate images at multiple voltage levels. That is, you can say that okay, my device will be excited first at 0 volts, then at 0.5 volts, then at 0.1 volts, then 1.5, 2 volts, 2.5, 3 volts, like that. At every voltage step it will capture the image, and this is how voltage series is generated, in contrast to whatever we have discussed, which is time series. Okay, so once we have understood the parameters of like the device control, the waveform selection, etc., we would have to select a proper folder in which the series would be saved. Okay, so once the measurements is started, you can always select a region of interest. Okay, by selecting a region of interest, you can monitor how that temperature averaged over that region of interest varies with time. So this ROI history will give you this value. Okay, and that will help you understand if your measurement data is properly captured or not. Okay. A very important aspect of getting these values correctly is to type in the value of the estimated thermo-reflectance coefficient here. So this value is reflected live when the measurement is going on. So you have to type in the average thermo-reflectance coefficient value that you have calculated in the first module. You type in this number, immediately the temperature will be shown here. If this number is wrongly typed, or you have forgotten to type the number, then this would show an arbitrary temperature value which will not be correct. So for monitoring in this window, you have to select a thermo-reflectance coefficient value that you have measured. Okay. Okay, so once we have generated the delay series, we can save it, and as I will show you in the image processing software, that what else can be done using the delay series. Okay, the next type of measurement is steady state imaging. The steady state imaging technique is a low frequency imaging mode. So in the transient imaging, it was of the order of milliseconds, right? Time scales. Here it would be the order of seconds. The device would be on for tens of seconds, then it would be off for an amount of time, and then it would be again on for tens of seconds and then off. So one cycle in this measurement corresponds to this on-off phase. Then the next cycle comes in, and the imaging happens. So how does the imaging happen here? A cold image of the device is captured in the off state, right? The device is off, cooling data is captured. Then with reference to that, the device image in on state is captured, right? So let us say you are looking at this cycle. So the cooling image will be captured here, then the heating image is captured, then again the cooling image is captured here, then again the heating image is captured. So the temperature during this heating image would be referenced to the pixel reflections captured during the cooling cycle. So pixel by pixel comparison of reflectivity will be done between the on state and its previous off state. Okay, and that is how the thermal image will be developed in the steady state imaging. Remember that here it is time averaged. So whatever you are getting, the image that you are getting is a steady state value, because it is because the device is on for tens of seconds, hundreds of seconds, and the image is averaged over that time scale. Okay. So as we increase the number of cycles, this significantly improves the temperature resolution. Okay, because if you are averaging over 10 to the power 3 seconds, or 10 to the power more than 10 to the power 4 seconds, you can measure temperature changes as fine as tens of millikelvin. Okay, even 30 minutes of averaging will help you achieve a temperature resolution of 0.1 seconds. This is important whenever you're looking for very fine measurements. Okay, software control is absolutely similar to that of the calibration module. You have to just ensure that the brightness is sufficient for high SNR. You have to select properly device on time, averaging cycle, duty cycle, etc. Then again, similarly, you have to select the 3D alignment, capture reference, and then go on with your measurement. Okay, now that we have done calibration, data acquisition, we'll go to data analysis and image processing softwares, which is a SANG Analyzer Plus. Okay, SANG Analyzer software is an integrated package which is used to, so this both image analyzer, the SANG View Image Analyzer is an integrated package which will help us to view the acquired images, the raw images, correct the thermal reflectance coefficients for thermal expansion related errors, which will be shown in the demonstration session. It will help us find area mean temperature values. For example, you select your regions of interest at multiple regions of interest and you compare the temperatures averaged over that region of interest. You can create and save temperature cross sections, and you can output the images in various formats. Interesting part is this transient image that you have captured, the transient image can be saved as a delay series movie, which you can view in normal AVI movie format. Okay, so if you quickly look into the SANG Analyzer software, so the first step would be to identify the various points. First is the file window wherein you can load multiple files. Then you see the reference CCD image shown here. You have the image calibration window here and the working image, that is, using this calibration image you open a thermal image and you use this calibration image to get the actual temperature. So this would be our working image, and all the numbers associated with the region of interest, for example thermal cross section, temperature of a particular region can be viewed in this part of the window, thermal cross section, ROI series graph, etc. The first step in this software is to correct for the calibration map, correct the calibration map for thermal expansion. So you have to load the calibration image, right? You have to load the calibration image here. Click on the correct XY, which is zoomed in here. So you clicked on the correct XY, and then you save the image in TTI format. Okay, so you have to go to the save images. You have to save it in TTI format. Once this is done, you have to then load the calibration image. So I'll go back. Once the correction is done, you load the corrected calibration image. So there are three types of calibration that you can use. First is point by point calibration. This is important for wherever you want a very good spatial map of temperature. So this uses the corrected calibration thermo-reflectance coefficient map to estimate the temperature distribution. The second option is coefficient masking technique. You select two distinct regions, that is, say you have the semiconductor, you have the metal. You select two distinct values of coefficient, and the processing will be done in these two distinct regions. That is, the temperature will be reported only from those regions where the CTH values are in between these two windows. And the third is you type in an average coefficient number. So you select this, you type a single average coefficient, and then the temperature will be calculated accordingly. But then material to material variation information would be lost. Okay, so we will use the first one, point by point calibration technique. We'll load our calibration image. Then we load our image series. Okay, we load the image and we view it in the active window. And then we process one by one by clicking on the data series. Left hand side of the processing window, you see there is something called data series. You click on process series, and then the calibrated image will be used to calculate temperature and each and every time instance of the series. And you get a transient of this form shown in the middle of the screen. You can then select multiple regions of the device. For example, you select one region here, one region to the above, below, like this, and then you can view the transients at each and every, how the temperature evolves at various points in the device. You can do that using this, selecting multiple regions of interest. Also, you can select a thermal cut cross section, like a vertical cut or a horizontal cut, and the thermal cross section will give you a view of how the temperature is distributed. Okay, so this shows that the software is very powerful. In addition to these, we also have other processing capabilities, for example hyperspectral imaging capability, because our devices are made up of multiple materials, and therefore we would need multiple wavelengths to characterize the temperature of our device, and therefore we have to use multiple wavelengths, and then this data has to be combined to generate one image. So that is done by something called hyperspectral imaging. This is not shown here, it will be shown briefly in the demonstration session. Okay, so what have we learned? If we summarize this whole presentation in terms of our learning outcomes, what we have learned is that we have got to know about the basic working principle of the thermo-reflectance based imaging tool. What does this tool do? This imaging tool accurately captures temperature distribution with a spatial resolution as low as 250 nanometers, a temperature resolution as good as 50 nanoseconds, and can detect temperature rise as low as tens of millikelvins, although albeit averaged over a large number of cycles. We then discussed three imaging modes, like 3 steps of imaging: calibration to estimate the thermo-reflectance coefficient. We went on to understand the various acquisition modes, the steady state imaging, transient imaging, and then we went on to understand how the data analysis and processing is done. This presentation is aimed at giving you an understanding of the working of this tool. The demonstration in the subsequent sessions will give you a feel for how the actual measurement is done. If you're interested to further dive deep into this measurement technique, these are a list of some references, and most of the material presented here has been studied, has been compiled from the NT220C manual that is available in this website. And you can also go through these papers based on this thermo-reflectance imaging module. Thank you so much for patiently hearing out.